The binomial probability distribution. This is a big deal in statistics and in probability. The binomial probability distribution, let's highlight, is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive or disjoint outcomes. The two outcomes are generally referred to as, and we're going to use this color scheme today, so if you follow along with me, successes, such as making a free throw, and failures, such as missing the free throw. So success, if you're flipping a coin, could be successfully flipping a heads, or failing to flip a heads if you get a tails. So you have essentially just two options of success or failure. Experiments in which only two outcomes possible are referred to as binomial experiments. The prefix bi means two, so two number, success, failure. That is green. Provided that certain criteria are met. And so here are the criteria for a binomial probability experiment. This is not like the criteria for the random variable last time probability. These are different sets of criteria. An experiment itself is said to be a binomial experiment if the following things occurs. If the experiment is performed a fixed number of times, so you say, I'm going to flip this coin 10 times, or I'm going to shoot 10 free throws. Okay? And each repetition of the experiment is going to be called a trial. So if I'm shooting 10 free throws, you have trial 1, trial 2, trial 3, trial 4, on and on. The trials are independent. This means that the outcome of one trial will not affect the outcome of the other trials. For each trial, there will be two mutually exclusive or disjoint outcomes. Again, we're going to call those success or failure. It's the only options. You either make it or you don't. You either get heads or you don't. The probability of success is the same for each trial of the experiment because they are independent. When we're talking through binomial probability distributions, the notations we're going to use is n to represent the number of trials. This is blue, by the way. N is the number of trials. P is going to represent the probability of your successes. And 1 minus P is going to represent the probability of your failures, which makes sense because probability has to add to 1. So 1 minus P is the complement of P. It's everything but the success, which would be a failure. If capital X denotes the number of successes in n independent trials of the experiment, then that means that each option will be between 0 and n. So if you're shooting 10 free throws, you will either get somewhere between 0 or 10 free throws in as a success. So first things first, let's just make sure we understand when experiments are binomial and when they aren't by going through the 1 through 4 criteria for each of the following scenarios. And if it is a probability experiment, meaning we can say yes to 1 through 4, we're also going to determine the possible values of the random variable x. So our first option is an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. Okay, how many times is the trial done? And if we can answer that question, we're good on number 1, that we have a set number of trials. He's going to shoot 3 free throws. The second thing wants me to know if the trials are independent. Does making a free throw depend on if you made the free throw before it? No. So these are independent. That's good. He's always going to have an 80% chance of making it. So that's good. I guess put little check marks here. The third thing that we need says for each trial there are 2 mutually exclusive or disjoint outcomes, success and failure. Let's define those things. What does it mean for it to be a success in this experiment? If he makes it. So that's good. We can define success. What does it mean for a failure here? He misses it. So if we can define a success and a failure, a yes and a no, then that is good for number 3. These are 2 mutually exclusive disjoint outcomes. You can't make it and miss it at the same time. The fourth thing that we need to check here is if the probability of success is the same for each trial of the outcome. Based on what they told us, what is the probability of success here? 80%, which means we would put 0.8. What is the probability of failure? 20%. If 80% is make it, that means 20% is not make it. And if we can define those and they stay the same for every trial, which they do, then this all four get check marks and it is a binomial experiment. Since it is a binomial experiment, let's write down the possibilities that we can get. So if the guy shoots three free throws, what's the options for number of free throws he could make? What are those options? What if he misses them all? So 0, he could make 1, he could make 2, he could make all 3. This is the options for that binomial variable. We need all 4 of these things to be in my criteria before we can determine that it is a binomial experiment and then think about the experiment itself, the outcomes. Letter B, we're going to do the same thing and try to find all of these 3 things. According to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Ridiculous. It's vanilla, everybody. Suppose a simple random sample of size 10 is obtained and the number of Americans who chose chocolate as their favorite ice cream flavor is recorded. Let's see if it fits the bill. How many times are we polling Americans? What's our sample size? So we have a set size of trials, a set sample size. Check for number 1. Number 2, are these things independent? Does you liking chocolate mean that you also like chocolate? Does it affect it all? No. So this is independent. Even though you're wrong, vanilla is the choice. Okay. Number 3, can we define what a success and a failure is? In this experiment, it would be a success if they like chocolate, or that's their favorite. So what would be considered the failure? Yeah, chocolate is not fave. I guess that's really not chalk is what we're going to say. If we can have a success and a failure, even though in my opinion, wrong, but it's a success and a failure based on the experiment, then we're good on number 3. Number 4 is that we have the same probability throughout each trial. So what is the probability of success? 0.28. What's the probability of failure? Ooh, 72, there it is. How did you get 72, by the way, if somebody's questioning that?
100 minus the 28.
Yeah, 100 minus 28 or 1 minus 0.28. So if we can define success and failure, boom, we're good. What is the values of the random variable here? How many people could I pull out of these 10 that like chocolate? Or let me rephrase that question. What's the least number of people out of the sample of 10 that could like chocolate? 0. And then I could get 1, I could get 2, I could get 3, 4, 5, 6, 7, 8, 9, and 10. That is the options. Now it's interesting, and I love that I've been saying this entire, I didn't even mean to make this point and drive this point home. Notice that I don't agree that chocolate is the favorite flavor, but I'm still calling that a success. So a success does not necessarily mean a good thing or the thing that you want. It's the thing that you're looking at. We're looking to see if we can predict the number of people who like chocolate. That's our success, even if success is something that's not positive, right? That's why we're using success and failure. What are we looking for in the experiment versus what are we not looking for in the experiment? Let's check the third one. A probability experiment in which 3 cards are drawn from a deck without replacement and the number of aces is recorded. So how many cards am I drawing? 3. Are these independent from each other? Let's think about this for a second. No, without replacement. So if I take a card out and I don't put it back, I have then changed the probability. We did this in chapter 5. I've changed the probability that I draw an ace in the second draw. So since this is not independent, full stop, this is not a binomial experiment. We're already done. It has to meet all 4 criteria to be considered a binomial experiment. And these are not independent. So let's see. This problem, it looks like it's a whole page because it is. We're going to see from start to finish, doing this all by hand before I teach you some shortcuts so you understand the formulas that you're using. We're going to construct an entire binomial probability distribution for the following example. It says, according to the American Red Cross, 7% of people in the United States have blood type O negative. A simple random sample size 4 is obtained, and the number of people X with blood type O negative is recorded. Let's construct from scratch a probability distribution for the random variable X. First things first. What is our sample size? 4. What will we define success to be? Now, what are we looking to find here in this experiment? That their blood type is O negative. That is our definition of our success here, if we have type O negative. Nursing friends, do you write O negative like that, or do you write like N next to the O for O negative? Do y'all know that? I actually don't know. That's why I'm asking. We're going to use this notation. If it's wrong, please forgive me. So what does it mean in our experiment if we have a failure?
It's not O negative.
Yeah, if it's not O negative. So if it's any of the other types. Maybe it's A, maybe it's B, maybe it's AB. Okay. Let's look at the probabilities here just to have all of this on our paper. What is the probability of our success? The probability of finding somebody with type O? 0.07. Very good, because 7% is 0.07, which means that the probability that we would not find somebody would be what? 0.93. Now, let's think back for a second here. If we were writing out our sample space like we did in chapter 5, sample space is S. This is how we started writing all of these things. I need to write down all of the options in this experiment. So let's say I start off and I find, bless you, in my sample size, I get real lucky and I find all 4 people that have type O. So we're going to call that 4 S's in a row for success, success, success. What if I get 3 successes and 1 failure? Failure. You see what I'm doing here? Let's draw out the entire sample space. Before we do that, how many numbers should be in my sample space when we're finished? Throw back to our counting techniques. How many options do I have for this place? Success or failure, right? So how many options? So 2 times 2 times 2 times 2 is how many?
8. No.
2 times 2 is 4 times 2 is 8 times 2 is... You should have 16 things in the sample space when you're finished. So let's find it. So after 4 successes and then a success and a failure, I could have 2 successes, a failure, and a success. I could have 2 successes and 2 failures. Can you finish drawing it out without me talking over your thinking? You should have 16 things when you're done with this. So we have the entire sample space here, which now feels like a little bit TMI, a little bit too much information. So my question for you, if we're looking at this right here, how many of our, this is going to be my random variable X. My choices are I found nobody with a success, 1 person with a success, 2 people with a success, 3, or all 4. How many people up here, frequency-wise, in my sample space had 0 successes? How many of these options? 1. How many of them had 1 success? And here's what I would do to maybe help this out. Maybe like cross them out whenever you've used them, right? Or the, huh? My marker is not changing. There's actually 4 with 1 success. So here's 1 success, 1 success, 1 success, and 1 success. How many have 2 successes? 1, 2, 3, 4, 5, 6. How many have 3 successes?
2.
I'm missing one. Oh, here.
4.
4. And how many have complete success? 1. Interesting. Okay. So we've got all of these things. What we're going to do is we're going to individually find the probability of each of these random variables because we need to fill out this table to make my probability distribution. So to find the probability of 0, we want to find the probability that it would work. So I'm going to use the frequency number, which I'm going to highlight in orange so we can see where I'm getting these numbers from. These are my frequency numbers, how often they happen. So I'm going to use that number, a 1. I'm going to then multiply it by the number of successes times its probability. So how many successes did I find for this first one? None. The probability of success is 0.07. What was the probability of failure? 0.93. And how many of those did if I had 0 successes, how many failures did I have? 4. Okay, again, 0 successes. That happened 1 time. So here's the probability of a success raised to the 0 power because it didn't happen. Here's the probability of a failure. How many times did failure happen in this example? 4. When we multiply this number together, we would get a decimal. We're going to round to 5 decimals. 0.74805. That is the probability that we would find no successes, no people with blood type O negative, if we pull a random sample of 4. Okay, what about the probability of 1? How often did we see 1 in my sample size? Sample space, 4. And the probability of successes happened how many times again? 1. Which means that the probability of failure happened how many times? 3. Do we see what I'm doing here? So I'm taking my frequency number. I'm multiplying by the probability of success times the number of successes. The probability of failure times the number of failures. I trust you to be able to type things in a calculator, so you get 0.22522. If I'm doing the probability of 1, probability of getting 2 people with O negative. What's the frequency of finding 2 people? 6, which means we're multiplying that by the probability of success, which my marker didn't change colors, times how many? Or to the what power? 2. And the probability of failure to the what power? 2. Now again, if you're like, why are we multiplying by the probability of success and failure? That's a great question. For me to get success, success, failure, failure independently, I would use the multiplication rule from chapter 5 to multiply 1 success times another success times a failure times a failure. I'm just shortening that into exponents so I don't have to write those numbers over and over again. We would get 0.02543. If I was doing the probability that I find 3 people with O negative, what is the frequency number? 4. Successes raised to what power? 3. And failure raised to what power? 1. If we throw that in a calculator, we would get 0.00128. And last but not least, the probability that we find all 4 successfully having O negative would be 1 multiplied by 0.07 raised to what power? Well, all 4. 4. And then our successes would be raised to what power? Our failures would be raised to what power? 0. Because we had no failures if they're all successes. This would be 0.00002. So these formulas here that I have, finding for 0, for 1, for 2, for 3, for 4, create this probability distribution that we were given in other chapters. We can fill in these numbers in our cute little chart. Now, what kind of pattern do you notice here? And I wrote these on purpose the way that I did so that you could see a pattern forming. What do you notice? What decreases?
As the frequency gets bigger, the probability decreases.
Okay, that makes sense because our probability of finding a success is 7%, so there's more of a chance for us to do a failure. So you're right, it will get smaller as we have more successes. Maybe look more in detail about these formulas right here. What patterns do you notice in here? Yeah, like the exponents, this one's going up because we're finding more successes, and this one's going down because that means there will be less failure. Interestingly enough, this pattern exists beyond just this particular example. If you flip your paper over, we can actually find each of these individually without having to write a sample space, without having to do all the things that we just did on this problem if you understand those counting methods that we did in Chapter 5. We zoom in here. You guys noticed that, we had this frequency, correct? This frequency number. If you're going to highlight like we did on the page, this one is orange. Here's your green successes. Here's your red failures, or pink failures. Okay. That number that was in front comes actually from finding the number of successes out of a particular number. That's a combination. So instead of having to write my sample space and count it, I can just do the combination of 4 choose 1, or 4 choose 2, or 4 choose 3, 4 choose 4. Then I can take that probability and raise it to a particular power I care about, and then the failure and raise it to whatever's left. This formula right here that's in this little box, the probability distribution function, is the shorthand for this entire problem we just did. We wouldn't have to make the sample space and count the frequencies and all of that good stuff if we know our counting methods to do that combination to find that first number. If you took my AP Pre-Cal class last year, this is also Pascal's triangle for binomial theorem of a polynomial. If you're expanding a binomial, we did this exact same thing. Probably don't remember it, and it's fine. I forgive you. Okay. When we're doing these kinds of problems, and I know we're probably not going to get to the actual problem until after lunch because I heard the warning bell go off. When reading probability problems, you're going to need to pay special attention to key phrases that translate into mathematical symbols, and people get these wrong all the time. If it says at least, that's actually the symbol greater than or equal to. So when you see these qualifying, not necessarily is or equal to, like that's obvious, maybe check this chart to make sure you're using the right way of the inequality sign that we're going to use. Okay, after lunch, we're going to try example 3, which is about chocolate. Chocolate. Do y'all know what that's from? It's from SpongeBob. Okay, great. There's still hope for you guys. We'll do this after lunch using the formula instead of doing all of that by hand. It'll be so much nicer. Right before lunch, we started to look at this problem because we now have a formula up here for finding the binomial probability distribution. So, according to the CTIA, which I actually don't know what that stands for, I should have Googled it before doing this problem, 72% of all adult Americans would rather give up chocolate than their cell phone.
Yes.
Crazy. In a random sample of 10 adult Americans, what is the probability that A, you would find exactly 8 that would rather give up chocolate? So before we go into that, let's go ahead and do our probability of success and failures. The probability of success, meaning you found somebody who would rather give up their chocolate than their cell phone is 0.72, which means the probability of failure not to give up chocolate over their phone would be 0.28. So to find the number of adult Americans, or the probability that you would find exactly 8, that means you are doing the probability of getting 8. So in my formula, the x value is 8. Okay, I can't show both because it's too high up there, but my x value is 8, p of 8. We would do p of 8 is equal to the number of adults in the trial, which is how many? 10. Choose how many? 8. Multiplied by my successes, 0.72 raised to that same power, 8. Multiplied by my failure, 0.28 raised to what power? 2. Because those exponents have to add up to the number of trials, 10. So that 10 choose 8 is giving me the orange coefficient, or the frequency from our problem before. And this is all stuff we can do in our calculator. Do you remember how to do 10 choose 8?
Yes.
Okay, in your calculator, please do 10 choose 8. Do we remember? You type 10. You press math, go to probability. It's option 3, then you type 8. What's that coefficient there? 10 choose 8. 45. Then we're going to multiply that by 0.72 raised to the 8th and 0.28 raised to the 2nd, which would give me 0.2548. So I did the whole formula in one. So 10 choose 8, which was 45. And 45 times 0.72 to the 8th times 0.28 to the 2nd. Okay, here's how questions will probably be asked, though. They like to ask these kinds of questions. What is the probability that fewer than 3 would rather give up chocolate? Fewer than, if we look at the translation here, translates to the symbol less than. Great, so this problem is actually wanting us to do the probability that x is less than 3. So question for you, what are my options that are less than 3? And 0. So really, it's like I'm doing the probability I would get 0, or I would get 1, or I would get 2. When we studied probability last chapter and you had an or statement, it's adding. We add the probability of 0 plus the probability of 1 plus the probability of 2, which is exactly what we're going to do. We're going to do 10 choose 0 multiplied by 0.72 to the 0 power multiplied by 0.22 to the 10th power. 28 with 22. What am I doing? Do we know where I got all those numbers from?
Yes.
It's the formula from the top of the page. Number of trials is 10. Number of successes is 0, which means the number of failures is 10. Then we're going to add 10 choose 1 multiplied by 0.72 to the first power multiplied by 0.28 to the what power? 9. Plus 10 choose 3 multiplied by 0.72 to the...
You mean 2?
Yep, I sure do. Let me put a 2 right there. Times 0.28 raised to the 8th power. I recommend for this one, on your calculators, just do each 3 piece individually and then add them together. So if we do 10 choose 0 times 0.72 to the 0 times 0.28 to the 10, you get a very, very small decimal. Round that to keep me 6 decimal points here so we at least have a significant digit. It'd be 0.1, 2, 3, 4, 5, 6. Okay, well, that's a 3, but I was counting the decimals. The second one, 10 choose 1 times 0.72 to the first times 0.28 to the 9th is 0.0000 0.076. And then the next one, 0.000881. When you add those together, you get 0.00096. Does anyone need to see the calculations on the calculator? Done up. These at least or at most feel like a lot of work, especially if you had one like this. At least 3 would rather give up chocolate. If you look at the word at least in the little chart I gave you for the inequalities, what symbol would that be? So we want the probability that x would be greater than or equal to 3. What are my options there? 3 through 10. So 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10. That means I would be doing this formula 8 times. Don't really want to do that. So let's think about this and let's work smarter, not harder. What is like the opposite, or shall I say the complement, of x greater than or equal to 3? Just less than, right?
Yes.
Didn't we just find x less than 3? So we can find the probability that it would be greater than or equal to 3 if we do the complement and we do 1 minus the probability of x less than 3, which we just found in the other problem. And I don't have to sit here and add together 8 different binomial probability formulas. I can just take that number I got in that other problem. That's too many zeros. And subtract it. So work smarter, not harder. If the numbers make sense for you to use complements instead of the binomial theorem, or if you want greater than 2, then that means you can do 1 and 0 and just do the complement. Like, work smarter, not harder. What about D? It says the number of adult Americans who would rather give up chocolate between 5 and 7 inclusive. Inclusive means including 5 and 7. So I would be like doing the probability that x is between 5 and 7. So what numbers are between 5 and 7 inclusive? 5 or 6 or 7. This one is for you to make sure you've got it. I've got you here. If we're doing or statements, that means we're adding. You're going to do 3 probability distribution functions for 5, for 6, and for 7, and then add them together. I recommend showing me the work like we did in problem B. Write down the formulas so that you know what you're typing in, do them piece by piece, and then add them all together. I'm going to pause and let you try. Okay, let's do a formula check. So we have 10 choose 5, 0.72 to the 5, 0.28 to the 5. 10 choose 6, 0.72 to the 6, 0.28 to the 4. 10 choose 7, 0.72 to the 7, 0.28 to the 3. When we evaluate each of those, we know how to evaluate it, yes? But the combinations? Okay. 0.0839 plus 0.1798 plus 0.2642, which altogether would mean this probability is 5279. Did we get that or get close? I might not have given you enough time to finish. So that's a lot of computation, yes? Individually doing this for each and every single one of these can be pretty bulky. So guess what we're going to learn to do? Oh, we're going to make this make sense for us. We're going to work smarter, not harder. What have we been doing with all of our formulas throughout this class? We did it by hand, so what's next? Excel. Go ahead and open your computers to your blank Excel document for this course. Let me show you how to use Excel to do a binomial distribution. And I already found a shortcut beyond this one that's in your notes, but I'll show this because it works every time. But when you have your formula open, wow, Excel open, hurry. Okay, so I'm here And before we really get started, let's go ahead and label our titles page, or our titles, the header. I opened a new sheet down at the bottom. So we're gonna make this, we'll go ahead and do the next example. So on your notes, example 4, we're gonna do that one, but we're following the instructions above it. So we're gonna say that we have a random sample of 15 adult Americans. So we're gonna do X and the probability of X. And we're going to do all the way through 15. Oop, not 25, 15. Okay, just so I can get the entire probability distribution done pretty quick. Now, the way that it's written in your notes totally works, and so we'll follow those instructions first. It says to click on the Formulas tab. The Formulas tab is straight up a tab like File at the top of your page. So you're going to click on Formulas, which is up here. You're going to go to More Formulas, functions, and then highlight Statistics. Statistical, sorry. Now it's on here, you can see it, you're using the binomial.distribution, right? That's what we're doing, so binom.dist, LOL. We're going to open that up, and it's going to ask you to use this this pop-up menu to answer the questions. Fill in the window. So we go to Formulas. More formulas or functions?
I'll click off of that. Yeah, that's what it was saying. Show formulas?
If you press on formulas, it doesn't open anything.
Yeah, it's open.
What's open?
The very last one that says ...
Um,
and then statistical. Yeah, I forgot Microsoft Online assumes that you know it, like what the headers are, but, and then binomial.dist. Okay, are we here? It says to fill in the window with the appropriate numbers. So the number that we want is actually this cell, because we want to find the probability that we happen to this once. So I'm going to type A2 right there.
It was binomial, right?
Dist. So again, number is what you're looking for. So for us, that number is in A2. What is the number of trials for example 4? Number of trials is 15. And it says the probability of a success is how much?
0.72.
No, we're doing example 4. 0.65. And in the cumulative, we're going to put false. Because that is going to help you find greater than or less than. If we're finding exactly this number, we're putting false. When you press enter, it's going to look like nothing happened, but it's because this number is so small. I can't see your screen from this far away. This number is so small, it takes a while for us to find an actual digit. That's why it looks like all zeros. Now the reason we're doing this, my friends, now that we can take this corner of this formula, we can pull it all the way down and it will copy the formula but change the value of the A. So notice A2, then A3, then A4, everything else stays the same. So now we have the entire probability distribution. That's all the stuff we did by hand in the last couple problems. This first actual question in example 4 says what is the probability that exactly 10 favor the death penalty? So we can go look on the row that we've made for 10 and find that number. What is the probability that 10? It's 0.2123. And if you're like, what are you writing down, Miss Quickly, because you're looking at your iPad? Good point. Here's what I'm writing down. I got this individually. That cell said equals the binomial distribution of 10 out of 15 trials with a 65%, but false because I'm not doing cumulative. That's what that cell was giving me. That's the formula. The second question here that says no more than 6 favor the death penalty. If I'm doing no more than 6, that means I'm doing x is less than or equal to 6 because it's no more than 6. At this point, we have two options. Because we've already done the entire distribution, you can take the number 6 and below and add them together. Very easy. You can write a sum or follow along with me, in a new cell to the side, we're going to go equals, and we're going to start typing binomial distribution and open a parentheses. Instead of going to that drop down or pop-up menu, you can actually just straight up type this in. The number that I care about is 6. The trials is still 15. The probability is still 0.65, but this time, since I'm doing below 6, I'm going to put true on cumulative. And once you put true on cumulative instead of false, it's going to add up all those values for you. And I just need to show more of my decimal. This is the same number you would get if you did the sum of 0 through 6.
So just go, where's your computer?
Okay, so this ends up being 0.04219.
Oh. For the probability is 0. You didn't put 0 point.
Oops, that shouldn't be a 10, that should be a 6. So again, here's the difference. If you're doing cumulative, sorry, I didn't realize I was not showing you the iPad. If you're doing cumulative, the no more than, that means adding everything before it, like a cumulative frequency from chapter 1. What? Chapter 2, just kidding. We are also expected to understand the mean and standard deviation for these binomial random variables. So we have new formulas for you. We're not going to have to do the big mess that we did last time to find the mean and the standard deviation. We have different formulas. The mean is found by doing the number of trials multiplied by the successes. The probability of the success. That's it. The standard deviation is the number of trials multiplied by the successes multiplied by the failure probability. Oh, but also take the square root of all that. Which is significantly easier than the mess that we did last time to find the mean and standard deviation. Those were crazy formulas that we had to do a lot of work for. So we're back to the chocolate example. Chocolate. According to CTIA, 72% of adult Americans would rather give up chocolate than their cell phone.
Okay,
In a simple random sample of 300 households, determine the mean and standard deviation number who would rather give up chocolate than their cell phone. Here's the things we need to know. What is the trial numbers? 300. What is the probability of success? 0.72, which means what is the probability of failure? 0.28. If we are finding mu, the mean, all we have to do is do 300 multiplied by 0.72. I'll put that in parentheses so it's easier to see. Which means that this is 216. The standard deviation, so how much spread this has, would be found by doing the square root of 300 times 0.72 times 0.28. We throw that in a calculator. Our spread here is 7.8. So finding the mu and the sigma the mean and the standard deviation significantly easier, in my opinion, when we have a binomial random variable, if we know the probability of success, probability of failure, and the number of trials that we're doing for that experiment. So let's start to put this all together. Because we need to start to draw some conclusions about this sort of information. So we're going to take the binomial distributions that we have and we're going to start graphing them. To graph a binomial distribution, first find the probabilities for each possible value of the random variable, then follow the same approach that was used to graph discrete probability distributions. Example A is completely done. What they did is they took the number of trials, 10, the probability of success, 2, thus the probability of failure is 0.8. And they found the entire table for you. We've also graphed it for you. Let's comment on the shape of the distribution. How is this one skewed?
Right.
Skewed to the right. As a little bonus, if you were having to do this one on your own, the formula you would use in Excel to do this would be the binomial distribution of whatever number from your table you're on, comma 10, comma 0.2, comma false. And then you would drag that down, all the way down your table. What we're going to do on this page is we are going to change the probability of success to see what happens as you get or increase your probability of success. So 0.2 means not a high probability of success. We're skewed to the right. We're going to do this same thing, so not changing the number of trials, but we are changing the probability of success. It's gotten more, right? This on a formula would be the binomial distribution of whatever number for a random variable we're looking at, 10, 0.5, and false. We would get the following table. To comment on the shape of the graph, I need to plot these points. Good old-fashioned plotting. We have 0, 0.001. That's going to be like, let me use a color so you can see what I'm doing. How about orange? It's going to be like here. 1, 0.009. It's also going to be like here. 2, 0.04. It's going to be like here. 3, 0.11. It's going to be like here. You see what I'm doing? 4, 0.2-ish. 5, 0.24. 6, 0.20. Ooh, that's not straight. Let me try that again. 7.11. What? 7.11? I didn't pause between saying those things. 8.04. You got 9 and you got 10. So we're just taking the probabilities and plotting them. And the reason we like to plot them is now we can make some conclusions about what's happening here. How would you describe this probability? Symmetric, also known as bell-shaped. So we increased the probability and it like shifted the centers. We went from having a lot of numbers low to a lot of numbers in the middle. What happens if I increase it one more time? We're not changing the number of trials, but we are changing the probability of success. And oops, this table is empty.
Whoops.
So here we go back to Excel. The formula we're going to use, I'll write it down first so you can try to type, is binomial theorem, or binomial distribution, sorry. Whatever the number cell you're using, 10, 0.8, comma false. So if you're following along with me on Excel, oh, can you get bigger, please? This one I only need to go through 10, so I'm going to delete the bottom cells, just go through 10, because that's the number of trials I have. And in here I am doing equals binom dist, open parentheses. I want to refer to the A2, so I'm going to type A2. The number of trials is 10. The probability this time is 0.8, but we are not doing this cumulatively, so we're putting false as the last one. Take the corner of that cell and drag it all the way down to copy that formula for all of your random variables. I'm not going to be able to show you both my Excel and my screen at the same time, so I'm going to pull my Excel away because you should have it on your screen. We have 0. Wait, I didn't even start at 0 on my table. Do you see my table not starting at 0?
Oh.
How dare I?
How dare you?
Good thing Excel is easy to edit. Oops, that's 0 again. How about 10, please? How about 8, please? I can type. We'll see. Okay, now I'm ready. So 0, I basically have 0. So I'm going to come in here, I'm going to plot the point, basically 0, 0. And then I have 1 comma, a whole bunch of zeros, so that's basically also 0. I have 2 comma, a whole bunch of zeros again, still basically 0. 3, and then it's 0.007, that's a little bit higher, we'll go up a little. 4 is 0.005, that's getting higher. 5 is 0.02, okay, we're making some progress. 6 is 0.08, all right, look at that. 7 is 0.2, oh, jump up. 8 is 0.3. 9.26. 10 is 0.1. Okay, I know that was a lot, but computer did a lot of the work for us. How would you describe this shape of this distribution? Skewed left. So what does this all mean? And why do we do this? We do this because we want to be able to have binomial distributions that eventually become bell-shaped, like this middle one. Because things that are bell-shaped or symmetric can be used with the empirical rule from chapter 3. So let's draw some conclusions here. This is what we did before on the other page. When we had a small probability of success, it was skewed right. When we had a relatively equal to like halfway probability of success, it's approximately bell-shaped. And we have a large probability of success, it's going to be skewed left. But what happens if we don't change the probability and instead we change the number? If we're changing n and we have a small n, it's going to be skewed right. If we have a medium number of n's, it's going to be slightly skewed to the right. And once we have a really large n, that's when we get our approximately bell-shaped information. So we want a large sample size so that we have approximately bell-shaped information. Specifically, for a fixed value p, so that's a fixed probability of success, as the number of trials n in a binomial experiment increases, the probability distribution of the random variable x becomes bell-shaped, specifically if you can multiply the number of trials times the probability of success times the probability of failure, and it's greater than 10. So if those things can be multiplied together and your value is bigger than 10, whatever it is, could be like 13, could be like 48, then that means that we can use the empirical rule to draw conclusions, which is eventually what we want to be able to do. What is the empirical rule? Do y'all remember this guy?
Unfortunately.
This is the empirical rule. It helps us determine, eventually, what is considered to be unusual. Unusual, what's the number we've been using for unusual? 5%. Something that is bell-shaped will be considered unusual if it is outside of 2 standard deviations, because 95% of all the observations are going to lie within 2 standard deviations. So if you look at the line that represents 2 standard deviations here and here, anything on the curve that is on the outside of those 2 standard deviations automatically is considered an unusual result. So you're looking for outside of 2 standard deviations, mu plus 2 sigma and mu minus 2 sigma. So if we go back to our chocolate example, according to CTIA, 72% of adult Americans would rather give up chocolate than their cell phone. In a simple random sample of 300 adult Americans, 230 indicated that they would rather give up chocolate than their cell phone. Is this result unusual? Okay, first things first, can we decide that this is bell-shaped? Can we use the empirical rule? Well, the number of trials is 300. The probability of success is 0.72. And the probability of failure is 0.28. We need to know if that special number exists that's bigger than 10 to tell us that this is going to be bell-shaped. So we do 300 multiplied by 72, or 0.72, multiplied by 0.28. Yep, we calculate. What do we get?
60.48.
Is 60.48 larger or equal to 10? Yes. So since that is a yes, we can use the bell curve to decide if something is unusual. We need to know these boundaries for unusualness. We will then do the lower limit of unusualness, is what I'm going to call it. The lower limit for unusualness is found by doing mu minus 2 sigma. And the upper limit for unusualness, 2 standard deviations away, is mu plus 2 sigma. Now we found mu and sigma in example 5. We had that mu is 216 and sigma is 7.8. So we just do 216 minus 2 times 7.8 and 216 plus 2 times 7.8. 1 plus 1 minus. So our lower limit for unusualness is 200.4 and our upper limit is 231.6. Anything beyond these limits on my bell curve would be in the 5% that's outside of the 95% confidence interval. So it would be considered unusual. So our number that we got, 230, is that unusual? No. Because 230 is well within, well, barely, but it is within these limits. So no, 230 is not unusual. We had to do a lot to get here. Binomial distributions have a lot of requirements. We have to be able to find them. We have to be able to find out if they are bell-shaped. And then we have to be able to find the lower and upper limit for 95% of the data so that the 5% that's unusual is outside on those edges.